This is a pre-recording ME502, and in this week 9 we're going to look at communication networks. So part of this chapter or this pre-recording, we will discuss the following topics. We will look at common industrial protocols, the future trend in industrial data communications. We will look at field bus, and then lastly communication network design and implementation. Starting with the common industrial protocols. So what is a protocol? It's a set of rules that two or more devices must follow if they are to communicate with each other. So the protocol includes everything from the meaning of the data to the voltage levels on that connection wires. So your network protocol defines how a network will handle the following problems and tasks: the communication line errors, the flow control, in order to keep the buffers from overflowing, access by multiple devices, failure detection, your data translation, interpretation of messages. Now, what was developed was the OSI reference model. In 1979, the International Standards Organizations, ISO, published the Open Systems Interconnection Reference Model, also known as ISO IS 7498, and that was to provide guidelines for network protocols. And this model divides the functions that protocols must perform into 7 hierarchical layers, and each layer interfaces only with the adjacent layer, and it's unaware of the existence of the other layers. So your OSI model further subdivides the second layer into 2 sub-layers, 2A and 2B, and that's then called medium access layer, or MAC in short, and logical link layer and LLC respectively. So there's the OSI reference model. So we have at layer 7 the application, then the presentation at 6, session at 5, 4 transport, 3 network. And then the second layer that we just talked about, which is now divided into 2A, which is the medium access, the MAC, and then logical link layer, LLC. Now in network protocols, the physical layer, which is now layer 1 right at the bottom, and your medium access layer, which is now sub-layer 2A, are usually implemented with hardware, while all the remaining layers are implemented in software. Now the hardware of this layers 1 and 2A are then generally referred to as modems. So that's the hardware that you'll see and we use for these layers, or transceivers, or drivers or controllers respectively, because that will normally control the flow of the data from the one device to the other one. Now strictly speaking, a network requires only layers 1, 2 and 7 of the protocol model to operate. And in fact many device bus networks use only these 3 layers. So the other layers are added as more services are required. For example, error-free delivery, routing, session control, data conversion. That's why they have been added. Now most of today's local area networks contain all or most of these OSI layers to allow contention to other networks and devices. So the 1, 2 and 7 is then 1 is the physical, 2 the data link, and 7 is then the application layer. So if you look at the 7 layers again, application, so that's the level that's seen by the user, so that's the user interface. Then 6 is get then to 7, that's the TCP/IP protocol. If you look at the TCP/IP protocols stack, then everything in blue is included in that stack, which means you can see 2 of the layers is not included. Now, one of the things that we see on that application layer is things like FTP, SMTP, HTTP, FTP. That's normally where you would store data files. SMTP, that's what you use for your my email, and HTTP, that's all the web pages that we would normally open. Then layer 6 is control function requested by the user. So data is reconstructed from other standard formats. So we have code and data conversion. So it translates between the different formats. For example, XML is an example what you'll find there. Then so data conversion can also be PDF, which is then well known. Then layer 5, the system-to-system connection, lock-in and lock-off are controlled on this layer. It establishes connection and disconnections. So it manages connections, control and disconnections of your communication sessions in more detail. And then those 6 and 5 is those that are not included in the TCP/IP protocol stack. Then 4, which is the transport layer, but that is a reliable data transfer between end devices. Your network connections for a given transmission are established by this protocol. So there you see TCP, UDP. Then the network itself, the outgoing messages divided into packets. Your incoming packets are assembled into messages for high levels. It's also established connection between equipment on the network. So that's where you'll find IP addresses we talk about. Then layer 2, that's your outgoing message are assembled into frame and acknowledgements. So we have some error detection, error correction. So that's the point-to-point protocol, PPP and Ethernet you'll find on this layer. And then right at the bottom, we have signal voltage swing, bit duration, electrical connections that established on this layer. So also referred to as bits on the wire. So looking at your protocol layer and data, so each layer takes data from the next higher layer. So there's the application layer, takes the data from that and creates a new data unit, so message, segment, frame, etc. So you can see it adds a header information to create a new data unit. Every time there's that header that's added as we go along. Now again, we only the 5 layers, and that's the 5 layers that's now part of the TCP/IP protocol that we are referring to, just to show you what happens in terms of going from one layer to the next. Now the same thing happens with the 2 missing layers, so we haven't shown it. So you see right on top we have the message, then we have the segment, then we have the datagram, and right at the bottom the frame. So then getting back to the 7-layer architecture. So for example, let's say the manager take a pencil and paper and he writes a message which he then gives to the secretary. That will then types the memo, puts it into correct sender and receiver address on the envelope. So that's coding and conversion, which sits at layer 6. She or he will then put a memo in the envelope. It fixes the correct amount of postage, takes it to the mailroom, which is now layers 5, 4, and 3 respectively. So that's where it will then be sorted and then go to the right place at the outgoing mail baskets, which sits at layer 2. Then your mail carrier physically picks up the memo, layer 1, and it will then deliver it to a physical address, and in this case it will be then an IP address, and then as it goes through the layers it will strip off the data that is specific to that layer, and if it has to do any operation on the application data, then it will also do that in the process. So whatever is done at the presentation layer on the left hand side will then be taken off on the right hand side, and that information will then be used to determine what needs to be done with the data coming along until it gets to the application layer, until then the memo has then been delivered to the manager on the other side. So there's just looking at the layering, the physical connection against only looking at the 5. So you start with the data right on top. We go through all the layers, every layer add some header and a new datagram. Then it physically goes through, let's say, a router. So that physically is where they are connected, but in that router we will also have link a network. So again, go through the same process, and then it gets sent to the correct address, because this router must now determine where this package needs to go. And there's 2 routes, this one and that one, but because of the IP address, the router will know and send it to the correct site. And then we start on the physical again. That's where it comes in, all the data gets stripped off, or all the additional information, and the data is delivered, or the memo. Now, the Institute of Electrical and Electronic Engineers, IEEE, Computer Society, established the standards. It was Project 802 in 1980 for the purpose of developing the local area network standard that would allow your equipment from different manufacturers to communicate through a local area network. Now, commonly used standards is 802.3, that's physical layer and data link layer media access control MAC of the wired Ethernet. Then 802.4 is the token bus protocol for a token passing access method of a bus topology. So only when you have the token, you can then basically send your message. Then we also have 802.5, which is the token passing scheme, which is then used in place of the carrier sends multiple access with collision detection on a ring topology local area network. So token passing instead of CSMA-CD. Now there's the standards. If you look at the IEEE 802 standards, so now again, that's now with reference to the ISO layers. So 802.1 is the relationship between sub categories. Pardon. So that's the relationship to higher layers. Then we have 802.2, logical link control protocol. And then as we go down, 802.3, that's that CSMA-CD bus, baseband and broadband. 802.4, token bus, baseband, broadband, in terms of the different speeds that it can handle. 802.5, that's the token ring. And 802.6 is metropolitan area network. So that's the MAN in short. So you can see in terms of layers where it falls in, 802.2 logical link protocol, that's a 2B. Then we have the others are 2A medium access control MAC and the physical layer. So that's layer 2 data link combined 2A and 2B, and then layer 1 physical right at the bottom as it's been defined. As you can see, broadband and baseband. Baseband is lower speed, broadband is then higher speed for all the different standards for IEEE. Now IEEE standard, which is ISO accepted as its own standard, regulates that layers 1 and 2A of your OSI model, and it specifies the network access should occur through CSMA-CD using a bus topology at the rate of 1 to 20 megabaud, that's baseband, or 10 megabaud in terms of broadband. And the widely used Ethernet network complies with the IEEE 802.3 standard. So that's 802.3. In control systems, Ethernet 802.3 network is primarily suited for non-critical applications, such as supervisory monitoring and PLC program management. Now, just to define baud as your modulation rate of data transmission, that's expressed in bits per second. Then the standard Ethernet, so there's 802.3, which we just described on this side over here. So layers 1 and 2A of the OSI model, CSMA, CD. So what you see here, in the old days when we still used coaxial cable, there was a 50 ohm line termination, 50 ohm resistor, and the topology is extended bus. So you can see it's like a tree structure, and we have baseband and broadband. The data rate 10 megabits per second. Coding is Manchester. Access method is then CSMA CD. So that's collusion detection. You can see special coaxial cable, and the distance between two nodes maximum can be 2.8 kilometers with this implementation. Now in the old days, that is typically what we have used, the coaxial cable to interconnect the different nodes. Okay, so that's your IEEE 802 and how it fits in with the different layers. So what we looked at now was 802.3, CSMA, CD, bus, baseband, broadband. So look at 802.4 and 2.5. 2.4, that's the token bus network at different baseband and broadband transmission rates. 802.4 is used by many PLC manufacturers as your protocol structure of the lower layers of the local area networks. And 802.5 specifies a token ring network with lower transmission rates for baseband cables, 1.4 megabaud. And IBM adopted that 802.5 standard for their token passing protocol with the ring topology. Now getting to 802.4 back again, so that's a token bus network at a different baseband and broadband rates than 802.3. And it's used mainly by the PLC manufacturers because the protocol structure of for that lower layers of the local area network. So there you can see the 802.4 standard token bus. Now you can see the token passing in the token bus. So this arrow indicates the direction. So, and you can see what we have here is a virtual ring. So that's how the token will pass along, and once the token is at a specific node, that node can then transmit the data. So it's a physical bus structure, logical ring structure. So you can see a virtual ring. Method of transmission, carrier band and broadband, 1 to 20 megabits per second. Coding is then frequency shift keying and also PSK. So this access method is token passing. Again, you can use coaxial cable, fiber optics, and distance between two nodes is then 800 meters. And we still have some line termination for this. So you can see it is a physical bus. So there's just another picture of showing the virtual ring, how the token will be passed along. 802.5 specifies a token ring network with lower transmission rates for baseband cables, 1.4 megabaud. And again, IBM adopted this for their token passing protocol. So this is how it looks like. So you can see it is a ring. It's got some trunk coupling units. So there's the connection point in the middle between all the rings. And we have a medium interface cable and a medium interface connector. So it's a physical and logical ring. Baseband, data rate 1, 4 or 16 megabits per second. Again, Manchester coding, token passing, twisted pair cable that we use, distance between two nodes 100 meters. So it uses a special 3 byte frame called a token that travels around this logical ring of workstation or service. So now again we will have the token traveling along, and as if you receive the token, then you can transmit your data. Now most manufacturers who offer Ethernet compatibility to implement supervisory functions over your equipment controlling plant floor functions use a TCP/IP protocol for layers 3 and 4 of the OSI model. And the transmission control protocol Internet TCP/IP was initially developed for ARPANET, a computer network created in the early 70s in the United States. but today it's utilized in Internet data networks. Now your TCP/IP protocol, the TCP part guarantees control of the end-to-end connections. So your TCP makes several services available to the user, such as establishment of network connections and disconnections, guaranteed data sequencing, protection against loss of sequence, connection time control, and a transparent multiplexing and transport data. The IP, the Internet Protocol, performs complementary functions such as addressing network data, distributing data packages, and routing data in your multi-network systems. Now, some of your PLC manufacturers offer programmable controllers with TCP/IP over Ethernet protocol built into the PLC processors, and that allows the PLC to connect directly to a supervisory Ethernet network. So, as I mentioned, some of your manufacturers offers programmable controllers with TCP/IP over Ethernet protocol built into the PLC processors. Now, one of them is the Allen Bradley's PLC5 controllers. That's got a built-in TCP/IP over Ethernet control, and which now is visible over there. And as you can see, we have PLC5 controllers. There's one, there's another one, there's another controller, and they can all link up with the control logic system here. So that allows the PLC to connect directly to the supervisory Ethernet network because of that capability. So you can see we use that's a control network, and then that's a DH plus network. All of them which use then the TCP/IP that use the Ethernet for connection. So there's another picture showing a PLC connected directly to an Ethernet. So there's a personal computer connected to the Ethernet TCP/IP network. We have a PLC with the Ethernet processor, as you've seen with the previous slide, and then a PLC with a LAN interface, which gives you the network node. This is a logical area network interface in between the personal computer and the network node, and they use local area network and Ethernet TCP/IP network for the interconnection. Now the Synamics Drive family offers both Profinet and Ethernet IP software stacks for Synamics G series, which is easily selected by a parameter setting in your standard Synamics firmware. And the communication options board and the control unit is required. That drives to communicate on the Ethernet IP. So if there is additional boards that are then available, which then allow this connectivity that you require. And control logic system that's similar to what the Synamics. So there we have our PLC. We've got a remote input output. We've got our human man interface. This is Synamics G120, which can seamlessly be applied in Profinet and Ethernet IP network connections. Then we have the network IP address of the Synamics G drive can be set through starter software, which found on that PC itself. So there's two methods of configure the Synamics G series drive to communicate over Ethernet IP. So focus on the Synamics approach to configuration using add-on instructions, but then you require version 19 or higher of the RS Logic 5000, and then we have the RS Logic Emulator 5000, which is a software simulator for the Allen Bradley line of logic controllers. So this just shows you the series configuration method. So you see right on top, set G120 IP address and subnet. So there you allocate an IP address, and then set G120 to Ethernet IP adapter. So that's how you will then set it up so that you can use it via Ethernet IP. Then sometimes the TCP/IP section in your supervisory network is replaced by another protocol, which is the manufacturer's message specification, MMS protocol, and that's used by plant floor devices to communicate through 802.3 networks. So in this configuration, your PLC can communicate with other intelligent systems such as robots and CNC machining centers. So there's MMS over 802.3 network, connecting the host computer to your PLC with a MMS 802.3 interface processor. These are CNC machine and also the robot that can now be interconnected with the MMS protocol. So it's an internationally standard ISO and messaging system for transferring real-time process data as well as supervisory control information between network devices or computer application, and this standard was developed and maintained by the ISO Technical Committee. So what does MMS define? A set of standard objects which must exist in every device on which operation like read, write, event signaling, etc. Then there's virtually manufacturing device, VMD. That's the main object, and all other objects like variables, domains, journals, files comes under VMD. Then a set of standard messages exchanged between the client and the server station for the purpose of monitoring and control these objects, and a set of encoding rules for mapping these messages to bits and bytes when it's transmitted. So that's what the MMS defines. Now we created a new version of MMS using Internet protocols instead of bottom 4 layers of the original stack, plus RFC 1006, ISO transport over TCP in the transport layer. So you can see there's the application layer, there's the manufacturing message specification, there's MMS, and the association control service element. Then for presentation, we've got connection-oriented presentation and abstract syntax notation. Then we have connection-oriented session, and a connection-oriented transport, and a connectionless network, and then MAC Ethernet and MAC token ringer, and the Ethernet line right at the bottom. Now with this new stack, MMS has become a globally accepted standard. Now MMS as an application layer protocol provides application services to the business function, not connectivity service. So if you compare the MMS view of your network application, you can see there you have the application function, MMS presentation session. On the common view of network application, this hidden network application function is where your drivers and glue and etc. where you'll find that. So right on top we have the business function, and then we have the two that differ between the MMS protocol and the normal view, and then right at the bottom we've got the connectivity functions. So with the MMS, the communication infrastructure is built once, then reused by all the other business function. So that's, if you want to justify MMS, it requires that the users recognize the value provided by the network application functions in facilitating things like interoperability, independence, and also access to data. Now what is the future trends in industrial data communications? Now there's a few things, some of them has actually been used a lot, but it all led to what we have right at the bottom, the IoT, as we all talk about it today. We have packet switch networks, pervasive networking, direct distance dialing, integration, new information services, and then IoT. The packet switch network is just the fact that the message is taken and divided into packets, and then each packet from the same message can take a different route as indicated in this picture over here, and eventually that will be all assembled at host 2 again. But before the fact that you divide it into packets means that you can use multiple routes to get the data over there, and that's why it has been developed. And instead of circuit switch, we now have packet switch networks. Then we have direct distance dialing, and that's provided for communication services platform. So a caller may dial a local number or a long distance number to access the communications platform, and the platform may provide plurality of the different communication services, including things like voicemail services, paging, automatic routing, facsimile message services, and expenses associated with servicing the call are then partitioned between the caller and the subscriber of the communication services platform in an intuitive and reasonable fashion. But that also led to voice over IP, so that by using that you can save. Then we have pervasive networking, which means network access everywhere. Exponential growth of the network use, many new types of devices with network capability, exponential growth of data rates for all kinds of networking, broadband communications, use circuits with 1 megabits per second or higher, DSL for example. Now looking at that, as you can see in the picture here, relative capacities of telephone, local area network, backbone network, wide area network, internet circuits, DSL, they have all increased since we started in the 80s. So to comparison, in the 80s we have 300 bits per second, which was then a small dust particle. Then we get to sand, which is about 9,600. Our modems, then we had our 56 kilobits per second modems, then we have DSL where we went into the megabits, and now we have radio that if you use LTE can go into the 100 megabits per second. So that was telephone and access. Then LAN and backbone technologies, so it starts like a sugar cube, 128 kilobits per second, so for the data, went up to 1 to 4, 10 megabits, 100 megabits, and even to 10 gigabits per second. Then the WAN and internet technologies, starting at 56, then going up to 1.5, 45 meg, 10 gig, and now 25 terabits per second. So because of the whole increase of data that has been sent along. So that is pervasive networking with the network access anywhere and the fact that you have very high speed communications available. Then the other big thing that happened was the integration, also called conversion of voice, video and data. So previously this was separate networks, and that will merge into a single high-speed multimedia network. First step was integration of voice and data. Next step, video merging with voice and data. Now again, this is things that's already happened today. Now it did take longer, but it's because of the high data rates that we need for video that, as you all know, we do that today. Then new information services, worldwide web-based. So many type of information services become available, and it will ensure equality of your information received over the World Wide Web. Application service providers, so providing and operating a payroll system for a company that does not have one of its own. Okay, today we refer to that as all being in the cloud, but so all those services are available. It also starts with actually this convergence, where you now could have a switchboard, but it sits on a server somewhere else, and that is now has now become the cloud, and you can have your own switchboard, but it's not physically on your premises. Information utilities, wide range of information services like email, web, payroll. The same thing, not just payroll, but also doing your taxes. You can also do it the same way. But getting back to what we are talking about is the industrial internet, and that's referred to as IIoT, Industrial Internet of Things. So that's in the process of radically changing the way of manufacturing operates. Now if you look at the Purdy diagram, now that started at level 5 enterprise. Now that level 5 is now IoT enabled governance and planning system. Then level 4 was your site business planning. That is now IoT enabled. In level 3, site manufacturing operations. That's now smart connected operations, IoT enabled. Then we have level 2, area supervisory. Now, basic control and process. Now, all of that has now become smart connected assets. So, IoT enabled sensors, instrumentation, controls, assets, and materials. So, you can see that is the next development. So it's time to rethink manufacturing architectures in the context of Internet of Things with the cloud and mobile workforce comprising digital natives that will not accept rigid hierarchies anymore, preferred freedom that your social networking has enabled. So I'd expect the systems that they use in their professional lives to mimic the way the systems they use in their personal lives function. So it's combined efforts of the provider and the user to start leveraging the power that smart connected assets and devices deliver to automate the business processes of manufacturing. So it requires maintaining the reliability and security of the older hierarchical systems, but with the flexibility and agility of today's technology. Now we're going to look at field buses just now. So your field bus based on RS485 differential signaling are from the 80s, although there's still a lot of them in practice today. So that's how long this technology has been around. Profibus, Modbus, etc. Now in the meantime, there was the CAN bus frenzy and its variants based on asymmetrical differential drive of very limited speed. Now the CAN drive creators should have asked RS485 drive manufacturers to make them resilient to higher voltages, which did happen at the end of the day. And the latest advancements relate to various implementation of real-time Ethernet, Ethernet CAT, Profinet, Ethernet IP, which we did touch on, PowerLink, Circos Free. So that is what also then happened on the industrial data communications front. Now getting back to field bus and the input-output bus networks. So we have advantages in large-scale electronics integration and surface mount technology, coupled with trends toward decentralization control and distributed intelligence to field devices that have created the need for more powerful type of network, the input-output bus network. And this new network let controller better communicate with your input-output field devices to take advantage of this growing intelligence that we have. So there's the I/O bus network diagram. So it allows the PLCs to communicate with your input-output devices. There's your PLCs. There's your devices at the bottom. Similar to how your local area networks let supervisory PLCs communicate with individual PLCs. So what happens is we decentralize control in the PLC system. So it means we have larger and faster control systems if we implement that. Then now the PLC LAN and input-output bus network, the connection between that. So your topology or your physical architecture of your I/O bus network follows the bus or extended bus tree configuration. So you can see there's the extended bus tree configuration. So your field devices, which in this case things like control valves, motor starters, photoelectric switches, push button stations, connect directly to either a PLC or a local area network. So it can connect to this I/O bus network because of the intelligence that's now built into it. So a bus is simply a collection of lines that transmit data or power. So with this configuration, decentralized control in the PLC system. So we have larger and faster control system. And the basic function of your I/O bus network is to communicate information with as well as to supply power to the field devices that are connected to them. So a large tree topology bus network that have many branches may have up to 2048 or more connected discrete field devices. So there is the connection. So going to your PLC adapter, the IOBus network scanner, there's the IOBus network, and we have our intelligent photoelectric sensor, and that gets power as well as the information that is sent across this network. Now, intelligent field devices that connects to the IOBus contains intelligence in the forms of microprocessors or other circuits, and these devices communicate not only the on-off state of the input and output controls, but very importantly also diagnostic information about operating states. And that can prevent IO devices from malfunction, and it can indicate when the sensor has reached the end of operating life, when it requires replacement. So there's an example of intelligent field device. So there's a sensor circuit, the inputs, there's a microcontroller, a network chip, there's a network receive transmit connected to the input-output bus, the data side as well as the power side for this intelligent field device. Now, for example, the photoelectric sensor, so it can report when the internal gain starts to decrease. For example, say that's got a dirty lens, or a limit switch can report a number of motions that it's performed. So that can prevent malfunction, and you then replace it at the right time. That's the advantage of it. Now, the majority of devices used in process bus networks are analog, while most devices used in device bus networks are discrete. Although device bus networks sometimes include analog devices, such as thermocouples, variable speed drives, that only transmit a few bytes of information. So there's the types of input-output bus networks. So we have our bus network that's then divided between device bus network and process bus network. The one being more discrete, and the one being more analog. Now on the device network side, examples is CAN bus, Seriplex, so low-level devices that are typically of discrete manufacturing operations. Then at the process bus network side, on the other hand, we have field bus and Profibus. The discrete side we can divide into byte-wide data and bit-wide data, only a few bits to several bytes, while on the process bus side, several hundred data bytes. So it handles a large amount of data, several hundred bytes. So your device bus networks include discrete devices. They are called byte-wide, that transfer 1 to 50 or more bytes of data at a time. And your device bus networks that only interface with discrete devices are called bit-wide bus networks, and that transfer less than 8 bits of data from simple discrete devices over relative short distances. So there's again a picture. Then on the process side, we have the Field Bus Foundation, Field Bus Standard, and then we have the Profibus Trade Organization, the Profibus Standard. On the device bus network, we have again the byte-wide, CAN bus, Interbus S, and then DeviceNet SDS. Then bit-wide, Seriplex, ASI, Interbus Loop. That's what we find on bit-wide side, what we use. So although there's no proclaimed standard for device bus network applications, there's de facto standards that emerge due to the availability of company-specific protocol specifications. And these network manufacturers or associations provide field device manufacturers with specifications, so to develop an open network architecture that can interface with many types of field devices. So in this way, each manufacturer hopes to make its protocol the industry standard. Getting back to byte-wide, and where we have DeviceNet, originally from PLC manufacturer Allen Bradley, which is now an independent spin-off association called Open DeviceNet. Other is then SDS, your Smart Distributed System from Honeywell, and they are both based on Control Area Network Bus, CAN bus, developed for the automobile industry. Interbus is another emerging de facto standard. Bit-wide, for low-end bit-wide device networks, like Seriplex, developed by Square D, ASI, your actuator sensor interface, developed by a consortium of European companies. And again, this is why I/O bus network and field device will specify compatibility with a particular protocol, even though no official protocol standard exists. So there is a variety that's available. Now, the main difference between device bus and process bus networks is the amount of data transmitted, and that's due to the type of application in which each is used. So your device bus network are used in discrete applications, which transmit small amounts of information, while your process bus network are used in process analog applications, which transmit large amount of data. And this is a nice picture showing it. So we have device bus, bit wide 1 to 4 bits, byte wide 8 to 256 bytes, and then process bus, as you can see, up to 1000 bytes. So that's why we say that the main difference is the amount of data that's being transmitted. Now, in terms of cost, your process bus network tends to be more expensive to implement than the device bus network, because analog input-output field devices are more expensive, and the intelligence built into a process bus is more costly than technology incorporated into the device bus network. Now, for example, the CAN, SDS, ASI, ASIC, and Interbus S chips used in device networks are readily available, standard off-the-shelf chips, which mean it makes them cheap, because there's such a lot being manufactured by availability, so that's why they're not that expensive. Then communication network design implementation. So we're going to look at network infrastructure, redundancy, installation cost, performance, reliability, and cost of downtime. So in terms of design of the networks, we must select the network topology. What we have is star 3 bus daisy chain. Now with the daisy chain loop, there's no redundancy. Redundant ring with redundancy if you use a ring. And then we have mesh. IP address assignment, BOOTP and DHCP. We can create broadcast limitations by a physical boundary of a subnet or by virtual boundary VLAN. And then security by controlling physical access and by controlling wireless access. So there's the bus topology. So all the different devices are connected to the bus. And then daisy chain, as you see, there's a connection from the one device to the other device. So if we have a break in the chain, then it means that whatever sits at the bottom cannot communicate, cannot send messages, cannot receive messages because of a break in the chain. The ring topology gives us redundancy, because if there's a problem over here, then it means if previously the messages were sent along that route, we can now send it from the other side. We can still reach all of them because of the fact that we've got a ring topology. In the star topology, as you see, this is the critical element. Because if that element's not operational, then you've got no connection to any one of those components. Tree topology. So the tree has actually got a star as part of it, because it looks like a branch now. Big branch with all the smaller branches coming out of it, but we now have 2 of them. And then the mesh topology. Now, mesh topology gives you again the redundancy, because if we have a problem with any device, then that normally there's a different path that you can use if you have mesh topology. Now, just looking at the redundancy, now what we have over here is a wireless redundant ring for industrial networks. So this is a ring, and one of the switches, let's say this one, set as a network master. So if for any reason one of the wireless links should be disrupted, then the managed switches will route the data in the opposite way. So for example, if there's a problem with this one, then it will basically just route it the other way. And so depending on where the device sits on the network. So it provides data path redundancy and dependable conductivity. And it, as you can see, for this example, it used wireless Ethernet. But because of factory floor applications run in real time, network must be available to users on a continuous basis with little or no downtime. So your manufacturers can help ensure network reliability using effective network design principles, as well as intelligent networking services. So your reliability needs to be considered at each layer of the OSI model, especially important for network design considerations layers 1 to 3. So if you look at reliability, one, physical. So what we can do in terms of reliability, redundant components, things like power supply, supervisors, etc., or redundant devices in terms of switches and routers. On the data link side, network topology, redundant links, redundant paths, and then networking itself, IP routing. So reliability exists at other layers, but is applied by automation and control applications. If you look at layer 4, that's inherently reliable because dropped or corrupt packets are automatically resent when detected by the protocol. So that's how the wider protocol actually then gives us reliability. But your overhead and delay presented in this process have led automation and control vendors to use UDP for some types of traffic. So it becomes more critical. Why? Because it's got less overhead, but no automated resending for particular information to communicate, and therefore relies upon the application to detect and manage packet loss or delay. So that's the difference between TCP and UDP. At the physical layer, a number of techniques can be applied. First, various components can be configured or purchased with resilient features such as redundant power supplies, redundant components such as fans, CPUs, network interface cards. Additionally, some devices may also support inline upgradability of your components or software, which will then allow continued service while the device being maintained. And these techniques will then significantly improve your mean time to repair. So using redundant devices may also help to maintain high network availability. So multiple switches and routers, if you configure them in a high availability manner, so that in case of the disruption of one device, the other device will take over and deliver the services. Data link reliability. So your manufacturer deploy an Ethernet solution. You should design networks with redundant paths so that a single device or link outage doesn't take down the entire network. So how the end devices and network devices are all interconnected is a network topology. And the two network topologies which we already looked at, most often used achieve higher availability are your ring and redundant star. And it's chosen also because it's got implication on wiring cost, complexity, performance, installation, and maintenance cost. Now here we have a redundant star topology network. So there's now a bit more detail than we had last time, and we have layer 2 and 3 switches. Now the access layer switches, which sits at layer 2, data link of the OSI model, and then we have the distribution layer switches, that is the access layer switches. Now your distribution layer switches may need to operate at layer 3 network of your OSI model, referred to as layer 3 switches or routers, and to support your VLANs, your virtual local area networks. Now here we have network connectivity can maintain over a ring via the opposite side of the device. So the ring is at the access layer and connected up through the distribution and core layers. So again, you see there's layer 3 switches compared to layer 2 switches that we have in the ring topology. Now if you look at recommended topologies, so if you look at the key concerns, if you want a high availability network with minimal convergence, high performance network with minimal bottlenecks, and straightforward network design, redundant star. So redundant star is then this one over here. Now redundant star, you can also see what star would just be one of these connections. Making it redundant is because they are connected through both sides, and we have a path in between the two. That gives us the redundancy. Then we have the ring. Cable complexity is a major concern. Highly available network is important. Cost is important. Then you can go for the ring, lower cost, but cable complexity. And then right at the bottom, cost and simplicity over availability and performance. You can go for trunk, drop, or bus. So all these network performance implications need to be considered along with the cost, complexity, and feasibility. So you can have a very high available, high performance network. Then you need to go to redundant star, but then you know it's going to cost you more. Now the key functions of network management as defined by International Organization for Standards. So performance management is gathering, analyzing, and reporting on a key network variables, including device and link availability, throughput and utilization, and user response time. That's what we do with network management. Configuration management is managing and updating network configurations, including operating systems versions, network parameters. Accounting management is managing user and device accounts. Fault management is detecting, logging, and notifying administrators of issues or faults. And then security management is controlling access to the network and monitoring the network traffic. So that's the key functions that we have in network management, and which we also need to apply to our industrial networks. Now lastly, getting to the network environment. The environmental factors such as heat, humidity, chemicals, vibration, electrical noise, and other kinds of electrical and physical interference will affect the performance of your network devices. So it is important to monitor and control the network environment with special attention to temperature, humidity, any water leaks, any chemical pollution, hardware deformation, or any loose connections that you might have. That's what's important in terms of networking environment. And that brings us then to the end of this pre-recording, which is week 9 of this module.